Hello and welcome, ladies and gentlemen. We are here in activity 5.1 of packet 5, and we're just going to jump right into it. Tiago and Leslie have been given the task of building an information kiosk at the zoo. They want to build the kiosk to be easily accessible from each of the various exhibits. 3 of the exhibits of the zoo are shown. So in the original packet, they don't have all these constructions here. This is something I've done ahead of time to save us some time. So number 1 says Tiago suggests building the kiosk so that it is equidistant from Giraffica and Primate Paradise. So he wants to build it so that it's equidistant from this point, Giraffica and Primate Paradise, right? So part A, Leslie says that the kiosk, that says for the kiosk to be equidistant from Primate Paradise and Giraffica, it must go at the midpoint of the line segment between the 2 exhibits. Is Leslie correct? Explain your reasoning. So she's saying, if we have this line segment, which I have here, she's saying that in order for the kiosk to be equidistant from Primate Paradise and Giraffica, it has to go right here, and that's the only possible place that it can go. So it's asking if she's correct. Okay. Well, one of the things that we've talked about, one of the things that we've conjectured is that every point along a perpendicular bisector of a line segment is equidistant from the endpoints. So if I put a point up here, it would be equidistant from Giraffica and Primate Paradise. If I put a point all the way up here, it would be equidistant from Primate Paradise and Giraffica, right? So what that means is this is not the only point. So is she correct? We'd say no. And then the reasoning would be that all points along a perpendicular bisector, so all points along a perpendicular bisector are equidistant from, oops, oh, I guess I have a pencil I can erase. I'm so used to doing pen, I just like scribble it out. That's my first reaction. There we go. From the endpoints of the line segment. Okay, there you go. And I know that's it's abbreviated. It's not like I don't know. If it is what it is, this is the explanation. I figured I'd write it out instead of just saying it in words, because I know sometimes I just explain stuff, and I know not all of you are auditory, and if I don't write it down, you struggle. But then if I do write it down, I have this thing where some of you guys just write it down and you don't actually listen to what I'm saying, so it's like a tough balance. Anyway, no, so all points along a perpendicular bisector are equidistant from the endpoints of the line segment. So I could put the kiosk anywhere on this line, okay, and then that would be equidistant from the endpoints. So B says use a construction to show all possible locations of the kiosk so that it is equidistant from Giraffica and Primate Paradise. Explain your reasoning. Well, B is to make this construction that I have, this perpendicular bisector right here, or this up and down one, and then explain your reasoning. Well, the reasoning would be that same thing we just said. We said that all points along a perpendicular bisector are equidistant from the endpoints of the line segment. Well, that's why this works. So explain your reasoning. We're good to go there. You'd want to say something similar, okay? So now on question 2, it's a little light, but you can see Leslie suggests building the kiosk so that it's equidistant from Elephantastic and Primate Paradise. Use a construction to show all possible locations of the kiosk so that it's equidistant from these two exhibits. Explain your reasoning. So I'm going to need to make another perpendicular bisector, but this time between Elephantastic and Primate Paradise, which you can see I have done. Okay, so here's Elephantastic, Primate Paradise. This line right here, this one from like top left to bottom right, or from bottom right to top left, depending on how you're looking at it, okay? That's that perpendicular bisector, so that's good to go. Explain your reasoning. Same thing, I'll say it one more time, okay? All points along a perpendicular bisector are equidistant from the endpoints of a line segment, or the line segment that it bisects, okay? So there you go. So now 3 says Tiago then wonders where the kiosk could be built so that it is equidistant from Elephantastic and Giraffica. Use the construction to show all possible locations of the kiosk so that it is equidistant from these 2 exhibits. Explain your reasoning. Okay, so here we go. Elephantastic and Giraffica. We make another perpendicular bisector here from bottom left to top right, or from top right to bottom left. Okay, so there you go. And then explain your reasoning. Same thing I've said the last 3 problems. Okay, so that would be that. There's your construction. Boom, good to go. So now 4 says describe how to determine a location that is the same distance from all 3 exhibits. Is there more than one possible location that is equidistant from all 3 exhibits? Explain your reasoning. So we want to find one point that is the same distance from all 3 of these locations. Well, I know that any point along this line, so I know any point along this line, okay, is equidistant from Primate Paradise and Giraffica. I know that any point along this line is equidistant from Giraffica and Elephantastic. I know that any point on this line is equidistant from Elephantastic and Primate Paradise. So if I wanted to find a point where it's equidistant from all 3, okay, then I would need to find a point where all three of these lines intersect. Now, luckily, we can see that right there. So this would be the single point, okay, that's equidistant from all three. And then it says, is there more than a single point? Well, if there's another spot where these three lines would intersect, then there would be another location, but we can see that as this line goes straight up and down, this line would get farther away down and to the left and up and to the right, and then this line would get farther away down to the right and up and to the left. So we can see that there would be no other spot where these three lines would intersect, so this would be the only possible place for the kiosk that is exactly equidistant from all three of these locations. Okay, and there's not more than one, and then explain your reasoning. Well, this is equidistant from all three because it's on a line, or it's on a point that's equidistant from each two. So like, because it's on this up and down line, it's equidistant from these two. Because it's on this line, it's equidistant from these two. Because it's on this line, it's equidistant from these two. And that combination means that it's equidistant from all three. And then why there's not more than one? Well, because these lines would never intersect again, and we can see that just by looking at them, okay? Cool, so then 5 says, verify the location you described in question 4 is equidistant from each exhibit. So we're just not going to worry about that one because this would just ask us to measure the points. Also, we did number 4, that's good to go. I mean, if you wanted to, you could take a straight edge and you could take a straight edge and you could measure these, and you could say, you know, I think these are, yeah, this is in centimeters, so you could say, oh, hey, look, that's 2, 4, 6, 7 centimeters away, and you could go, hey, this is, hey, look, that's 7 centimeters away, and you could do that, but just for the sake of time, I'm not going to, even though I kind of just did. Okay, so now we're on to number 6. It says you constructed a point of concurrency using the perpendicular bisectors of a triangle, right? So now, remember, 3 or more lines that intersect are called concurrent lines, and the point where they intersect is called a point of concurrency. So that is exactly what we did. We constructed a point of concurrency using perpendicular bisectors of a triangle. So 6 says construct the 3 perpendicular bisectors of each triangle. This would take a lot of time for me to do on video, so I went ahead and did it beforehand. You can see I have all of these, okay? All of these done. Now 7 says make a conjecture about the location of the intersection of the 3 perpendicular bisectors of any triangle. Is the intersection located inside, outside, or on the triangle? So I'd say, because the first one, okay, so the first one was acute triangle, not equilateral, obtuse, right, and then equilateral. So I'd say acute. I'll go NE for not equilateral. I'll go equilateral, obtuse, and then right, because there are 4 types of triangles that I drew these for. So then my conjecture about these would be that the acute one, okay, this acute one is on the inside, so I'd say that they're probably always on the inside. Looking at my equidistant one, also on the inside, so I'd say inside. Obtuse up here, that one's obviously on the outside. Right triangle, this one looks like it is on the triangle, right? Right there. So we would say on. Okay. There you go. So these are not formal conjectures. I did not write these assumptions all the way out, but this is just kind of a shorthand that say for my acute non-equilateral triangles, I'm going to assume that their intersections here with these perpendicular bisectors are on the inside. With equilaterals, I'm assuming that they're on the inside. Obtuse, I'm assuming they're on the outside. And right, I'm assuming that they are on the triangle. So there you go. Okay. On to the next one. So here we get a new word, the circumcenter of the point of the circumcenter is the point of concurrency of the 3 perpendicular bisectors of a triangle. Okay, so circumcenter, that's a new word. Okay, there's your definition for it. So 8 says consider the 4 triangles and then the perpendicular bisectors you constructed. So now A says measure the distance from the circumcenter to each vertex of the triangle. Is the circumcenter always, sometimes, or never equidistant from each vertex of the triangle? Explain your reasoning. Okay, well, for the same reason, so I wrote always here, and that's for the same reason that the zoo example works. Okay, so here's the zoo example. We said that this point is the point that's equidistant from these two, and these two separately. And so by putting your location on the point of concurrency here, you're going to be equidistant from all 3. And so by doing that same process on all of these triangles, you're also going to have, it's also going to be equidistant from all of the vertices, okay? And remember, a vertex is the points of your triangle, right? So that is always going to be true. That's always going to be true, okay? And to explain your reasoning, basically what I just said there, okay? So B now says measure the distance from each perpendicular along each perpendicular from the circumcenter to each side of the triangle. Is the circumcenter always, sometimes, or never equidistant from each side of the triangle? Explain your reasoning. So now it's saying instead of going from circumcenter or from this point of concurrency to vertices, it's saying to go from point of concurrency to the nearest side and measure that length and say whether that is sometimes, always, or never equal. Okay, it looks like in this acute one, these two look pretty close, but this third one's not the same. So that is a no. These ones look like they are all pretty similar. I'd say that this one is probably a little longer than this one just by looking at it. So I'd say probably still never so far. Okay, this one is on one side, and so any distance to another side will make this not true. And then the one that kind of saves this, okay, is the equilateral triangle, because this distance from here to here, from there to there, and from there to there is all the same. So we can't say never, because with an equilateral triangle, it looks like it appears to be true. So then we would say that this is sometimes true. And then to explain your reasoning, you could say how that the equilateral is the only triangle where this would be the case. Okay. So now step 9, revisit the triangles with perpendicular bisectors. Use the compass to construct the circumscribed circle of each triangle. So what you need now is you're going to use your compass. You're going to put the point of your compass on the intersection that you created, and then you're going to make your compass as wide, or you're going to put your compass to the nearest vertex, and then you're going to draw a circle around that. And I'm only going to do one just for the sake of time here, to kind of give you an idea of what it should look like. Okay, so there you go. So that's a circumscribed circle, and you can see that I actually have little baby gaps in between the vertices in my circle. And so if you do this perfectly, if you do it perfect, if you get your point of concurrency in the exact right spot and you set your compass to the exact right length, all of these vertices will be exactly on the circle. And you can see that mine is super close, so like we're good here. But just so you guys are aware. And then so you'd want to do that same process, okay, where you're putting the point of your compass on your point of concurrency and then setting it to one of your vertices, and you'd want to draw a circle around it. You're going to do that for all of these. Okay, one note on this obtuse one, if you don't want to do the whole triangle because it's going to be gigantic, like it's going to go into all 4 of these, that's how big it's going to be. If you just want to do the part where it touches all 3, you can do that, that's a-okay, right? Okay, so now on to number 9, or that was number 9, excuse me. Okay, so 9 was revisit, boom, okay, and then 10 says, what does the circumcenter tell you about the relationship between circles and triangles? Okay. So what does the circumcenter tell you about the relationship between circles and triangles? Explain your reasoning. So this one can be a little hard to see, but basically all triangles can be circumscribed by a circle. Or if you wanted to put it differently, any circle can have 3 points in it that we can connect to form a triangle. So if you remember in the last packet, we were talking about a property of a triangle where any two sides that you add up on a triangle have to be larger than the third. Okay, that is still true. That is always true. And so if you put any 3 points on a circle, let's see, any 3 points? Yeah, any 3 points on a circle, it'll create a triangle. So basically they're related in that way. So I just wrote it this way, that all triangles can be circumscribed by a circle, because if we take the perpendicular bisectors of any triangle, okay, we'd find the circumcenter, we'd find this point, and we could draw a circle around it. Okay, there you go. So that was activity 5.1 here in packet 5. I hope you all have a wonderful day. I'll catch you in class. Adios.